Hi, my name is Jim Williams, and I'm here today to talk about minimizing switching regulator residue in linear regulator outputs. You can download this presentation and more detail in App Note 101 at www.linear.com. Let's get started. People want to regulate the output of switching regulators with linear regulators to produce nominally a pure DC output. In fact, the output of the switching regulator is composed of switching regulator low-frequency ripple residue along with very wide-band harmonic residue associated with the switching intervals of the switching regulator. The linear regulator has restrictions on its ability to regulate high frequency and ripple content. You can see the ripple rejection starts out at low frequency at around 60 dB, and by the time you get out here to a megahertz, it's 25 or 30 dB. At 100 megahertz, which is where the switching content is, there's almost no regulation at all. What do we do about this? Let's take a look at the first slide in greater detail. First of all, the filtering components have parasitics of their own, series, inductance, and resistance. Even if you use a series inductor to make the filter capacitor more effective, the parasitic shunt capacitance defeats the purpose of the inductor at high frequency. The regulator has parasitic internal paths basically from everywhere to everywhere, and the output filter components suffer the same problems that the input filter components have. So the monitoring oscilloscope looking across the load sees stuff that you don't want to be there. This is a typical display that you'll see on an oscilloscope. This is the input ripple. This is the output so-called regulated ripple. You can see that the ripple content is down, but the spikes are very much in evidence. If we increase the value of the output filter capacitor, we flatten out the ripple, but the spikes pretty much stay the same. How do we get rid of these things? The secret sauce is to put ferrite beads ahead of the filter capacitors at both the input and the output of the regulator. Here's what happens when you put a ferrite bead in the input of the regulator. You see dramatic reduction below 5 millivolts peak to peak. If we place another ferrite bead at the output of the regulator ahead of the filter capacitor, you get further reduction. Let's take a look at this in detail. So now we've got a faster sweep speed and a much more sensitive vertical. And you can see that we've got less than a millivolt of wideband content, a marked improvement because of the ferrite beads. When you take a measurement at this sensitivity, it's always wise to sanity check yourself by probing coaxially the ground plane at the point of measurement. In theory, there should be nothing here. In practice, there's about 100 microvolts worth of common mode residue. That's acceptable in a measurement where the true error amplitude is as high as this is. We get a lot of questions from people about how we measure at these sensitivities, at these bandwidths. Basically, we take a 50 ohm noise limited amplifier and pipe it right to the oscilloscope. We connect the input of the amplifier via a coupling capacitor to the regulator under test. It's essential that this connection chain be made purely coaxially because we're at high frequency at very high sensitivity. If you do everything right and button it up, you get the waveform we had in the last picture, which is repeated here. If there's as little as 1 or 2 inches of non-coaxial ground connection in this chain, the waveform degrades to this presentation, which is basically useless. You have to have a purely coaxial measurement path. You can get more detail on this information in App Note 101, which you can download at www.linear.com. Thank you for your time today.